yesterday in our group activity, I hope you feel much more confident using the DAB-C to graph. What we're going to do today is now look at real-life situations. Basically, anything in real life that repeats itself in a cycle can be modeled by a sine and a cosine graph. So it's actually one of the graphs that has very, very many applications. Anything that goes in a circle, anything that goes around, an engine has a piston that goes up and down. You want to create an equation for that piston, you're going to have to make a sine or cosine graph. So the first example we have here is in a harbor, because with the oceans, there's tides. Tides go in, tides go up. Tides go in, tides go up. So they make a graph that's a sine or a cosine graph. And in this question, they give us the equation. They have a certain harbor, and they have calculated the depth of the water with a cosine function as given. What we have to do is we have to sketch a graph of this. So we're going to use the same things that we did yesterday. We're going to use our DAB-C to graph this equation. So first of all, we would notice that our D value is at 13.7 and our A value is 4.5. So I'm going to pick somewhere on my y-axis to mark 13.7 and draw my center line or my sinusoidal axis. I can then use my amplitude. So check mark, did the D value. My amplitude, remember we use our amplitude to mark our maximum and our minimum. So if I go up 4.5 to 18.2 and down 4.5 to 9.2. And the other thing that I'm trying to do while I label things on my y-axis is provide somewhat of an accurate scale. It doesn't have to be perfect, but I tried to measure so that my 9.2 is about double this 4.5. I tried to do a little bit of mental math in my scale so that everything was proportional a little bit. Like, it doesn't have to be perfect, but I chose my spacing to be somewhat proportional. So that's our A value. Okay. Our B value finds our period. Our period is always 2 pi over our B value. In this case, our B value is 0.16 pi. If we go put that into our calculator, it comes out to 12.5. So apparently, it looks like the tides go in and out every 12 and a half hours. So again, what do we do with our B value? Once we figure out our period, we mark 12.5 and divide it into 4 equal sections. So this will be 6.25, 3.125, and 9.375. Normally we would do the dash next, where we draw a dotted line without the shift. But if I look at this equation, can you see that there is no shift? So we technically don't have to do the dash without the shift, because as soon as we draw the graph, we'll be done. Now, this graph is a cos graph, and there's a negative, meaning there was a vertical reflection. Cos graph normally starts at a maximum, but because of that negative, our cos graph is going to start at a minimum. And it's going to go minimum to center line, to maximum, to center line, back to minimum, and we're able to draw this graph. Part B of this question says there's a bulk carrier. This is translated to a big ship. There we go. Easier words. there's a big ship that's coming into the harbor. It needs at least 14.5 meters of water, otherwise it's going to get stuck on the wall. How many hours per cycle can this big ship come into the dock safely before it gets stuck in the mud? So what we're going to do is we're going to go back to our graph, and a couple things we didn't do on our graph that we should have done is we should have labeled that our y-axis was our depth, and this was a depth at our units in meters, our time in hours. And if I mark, and I'm going to use blue for water and everything, if I mark where 14.5 meters is, and I draw a dotted line across here, does it make sense that it's only from this point to this point? In other words, where I've highlighted this in yellow, that's the only part where the water is deep enough for this ship. So I'm going to show you how we can use technology to find that. And there's two different ways we can use technology. Some of you might have a graphing calculator, so I'm going to show you the graphing calculator. For those of you that do not have a graphing calculator, I'm going to get you to take out your cell phones, and we are going to use a program called Desmos. Desmos is an app. You can download it. So even if you have a graphing calculator, some of you might also want to, on your phone, download the Desmos app as well. D-E-S-M-O-S. So you can go to the App Store. It's free, which is nice. And what we're going to do is we are going to type in, either in our graphing calculator or in Desmos app. Desmos, there is a button for pi as well. With both the graphing calculator and Desmos, we'll use x instead of t. So I type in the equation exactly as was in the question. So in the question, negative 4.5 cos 0. Oh, I typed it in wrong. Let me type it in right. 0.16 pi. Plus 13.7. And in Desmos, you can move your screen around to get the graph to show up. So I'll do all the instructions with the Desmos app first, then I'll do the same instructions with the graphing calculator. You can try to do it on your graphing calculator as well. So we want to find out when the depth is at 14.5. So we go to a second equation and we type in y equals 14.5. Ooh, how do I change the color? I don't know. There, it's blue now. There we go. On Desmos, this is how easy it is. Once you've graphed the original equation and you graph 14.5, you just bring your cursor close to like an important point that you would like to find, and sure enough, there they are. They'll automatically highlight. If you click on any graph, it'll automatically highlight important points. Here, you see it also highlighted my y-intercept for me. So from 3.48 to 9.02 is how long it would be safe. So I can write that in. We figured it out. Subtract them. We can write a statement. It would be safe for about 5.5 hours. Now, if you have a graphing calculator, we can do the same thing. We go to y equals, and we type into equation 1, negative 4.5. We have to make sure that our calculator is in radians. Desmos was automatically in radians for us.
Excuse interruption, staff and students. Just to let everybody know that this afternoon, starting at 1, there will be no bells in the afternoon, so have to just look at the clock for class changes. Secondly, in the afternoon, after lunch, cafeteria will be closed. You can still purchase stuff and be there at lunch hour, students, but after lunch, the cafeteria will be closed. Okay, thanks very much.
Now, with your graphing calculator, normally when you graph, so I'm going to go back to the graphing calculator there. Normally when you graph, it'll come up and the window will be set and you might only see a little part of your graph. But unlike Desmos where I could, right, on Desmos I could sort of drag my screen to see what I wanted. On your graphing calculator, in order to see the screen that you want, you have to go to the window button. And when figuring out the window button, you can look at our original graph. So in our original graph, notice on the x-axis we graphed just past 12.5, and on our y-axis it went up to 18.2. So when I go to my graphing calculator, I'm going to want to make a scale. I'm going to have my x-min just start at a negative number, but go up to, say, 15. That's a little bit past 12.5. That should be nice. The negative 1 is nice because it lets me see my x or my y-axis. If I start right at 0, then that axis line is like on the edge of the screen. It's nice to see it a little bit. Same thing with y-min. I'm going to go and start at negative 1 and go up to 20. Oops. Negative 1. You make sure you use the right negative sign beside the enter. And go up to 20. Now this x scale and y scale, if you want to play around with that, you can. Like for example, on the x scale here, you see how our ticky marks are every 3.125? I can actually type in 3.125, and now when I hit graph, I have exactly those ticky marks along the bottom. Has the same curve that I have in y2, I put 14.5. Now, unlike Desmos where you could just click on a function and it would show up where they intersect, on your graphing calculator, these have to be calculated. So above the trace button, it says calc, so we push the second button and trace. And then if you go down to number 5 is where they intersect. So push enter, and then if I enter on the first curve, enter on the second curve, enter on the guess, it will find the 9.02. It will always find the intersection closest to what your cursor was. So if I want to find this second one, you have to do it again. Second, calculate, number 5, where do they intersect? But I'm going to need to move my cursor closer to that second one. And once I'm closer to the second one, I can push enter, enter again, and it will find the 3.48. There will be some times on tests that I will get you either to use a graphing calculator or Desmos to solve it. So if you liked like I would say, get used to the Desmos app as well as your calculator, because it's very nice to be able to just, like on Desmos, once I click on here, this point automatically shows up, this point automatically shows up. And that's a little bit quicker. Now, once you get to university, most likely they're not going to allow you to use your phone on an exam. Most likely. They also, in a lot of classes, do not allow a graphing calculator, just a scientific calculator. I'm not going to give you enough time to write this down, but I'm going to walk through how would you go about finding these 2 blue points if you just had to use algebra and a scientific calculator. Okay? So first of all, we know that the depth is 14.5. So as far as solving for this, you could plug in 14.5 for the y value. And now you have to solve this equation we want to solve for t. The first thing you would do is get cos by itself. Move the 13.7 over, divide by negative 4.5, and you get cos by itself. You've solved equations like this before, but usually it was something nice inside the cos, like a cos theta. This is on the video, so if you do want to see it later, I'm not going to give you enough time to write it down. And you can copy it out later from the video. So, a strategy that's sometimes used in equations like this is if it's easier if this is just a theta, temporarily do a substitution and say, let theta equal the whole thing on the inside, then I get cos of theta is this. You can use your cast rule, get your reference angle. Cos is negative in quadrants 2 and quadrants 3. So we could solve what is theta in quadrant 2, what is theta in quadrant 3. After you've solved what theta is in quadrant 2 and quadrant 3, then you could substitute back, and that would allow you to solve for t. And you get the same 3.48 and 9.02 as we had before. So this is how you would solve it. Probably in a university class would require you to solve it by hand and just use your calculator with sine and cos. Okay, second question. We have a Ferris wheel. For those of you that don't know what a Ferris wheel is, it is, here we'll draw a picture of one. Big circle. Oh, that's too big. I didn't want to make it that big. Lost my support. Pretty big circle. There we go. And it has chairs on it. And you go around and around and around. And if you're scared of heights, it's really scary at the top, not so scary at the bottom. If you're not scared of heights, it's a pretty boring ride. It's not going very fast, but you get to see lots of stuff when you're at the top. So we're going to imagine, here we go, we'll make a little person. Oh yes, and they are happy. Here we go. And, oops, don't want to decapitate them. There, and they're sitting on there and they go all the way around on the Ferris wheel. So this is what we are imagining. We are imagining this Ferris wheel, and what we have to do in a lot of these real-life questions is we have to apply what was given into the equation, draw a picture of it to sort of visualize what's happening, and then make a graph. So in this question, okay, Ferris wheel has a radius of 15 meters, rotates once every 20 seconds. Makes sense the passengers get on a meter above the ground. Ferris wheels that go into the ground are not very much fun. Dangerous. And it makes sense that you get in on the bottom, not get catapulted up to the top or something like that. So when we draw a picture of this, and so right beside here, I'm going to draw my ground, and I'm going to mark 2 meters and say, I know that's where I'm getting on. If it takes 20 seconds to rotate, I can mark a place here at 20 seconds, and I know that I'm going to be back at the bottom again. Since it's repeating itself, this is going to make a sine graph. Does it make sense that if it takes 20 seconds to go all the way around, at 10 seconds, that's where you're going to be nervous, there at the top. Okay? So, I have 10 seconds, but I need to figure out what to label as my top point. How high will you be? 32 meters. And we can figure that out because the question told us the radius was 15 meters, okay? So that would make this 15 meters and this 15 meters. 30-meter diameter from 2 will go up to 32. Yes?
Why are we using 2?
Oh, 2. I don't know why we're using 2. Because it says we got on at 1 meter. No idea. So this should be a 1, and which would make this a 31. That makes a lot more sense, doesn't it? And from that, we can also figure out our middle. Does it make sense that we can figure out our middle to be 16? This will be our center line at y equals 16. As a result. And you could probably figure out then, oh, if it's a sign graph that should be divided into 4 equal sections, so I can mark this as 5 and 15, and this is where I'll be at the center line and at the center line. I probably shouldn't have my graph go back in time, just starting at 0. And this is what our graph would look like. And if you can draw the graph, then you can find its equation by undoing, right, dab C. So I can write off to the side, can I figure out my D value? Can I figure out my... And really, we only need to figure out the D, the A, and the B, because the C value changes if you choose to make a cos graph, a sine graph, a negative cos graph. So we're going to look at that. But first of all, can you see that we've done enough work to figure out our D value is 16. That's our center line. Our amplitude is the same as the radius. That's going to be 15. And our period shows up on our graph. It's 20. Your B value is always 2 pi over your period. And you could reduce that to pi over 10, but I actually like to keep it as 2 pi over 20, because then the 20 means something. It's your period. 20 is the period, so we write 2 pi over 20. Now, if I was writing an equation for this, probably the most common equation would choose this as a starting point. What kind of graph starts at a minimum? That would be a negative cos graph. Your amplitude is 15, cos. Your B value is 2 pi over 20. And if I use this, there's no shift. And my center line is at 16. So that would be one equation you could use. Another typical equation would be to choose, I'll color code this, if you choose the maximum. Which graph starts at a maximum? A cos graph starts at a maximum. So now I would have y equals, the 15 would stay the same, but now it would be positive. Cos. Your B value would still be 2 pi over 20, but now we have a shift. Your D value is still 16. The maximum is 10 units to the right, so I show that by writing an x minus 10. I could also graph a sine graph, and I'd say to myself, well, where does a sine graph start? At the center line going up. So I hope you start to realize that your A value, your B value, and your D value do not change. Whether you make a sine graph, cosine graph, doesn't matter. Negative cos graph, doesn't matter. What does change is your starting point. If you were thinking of a sine graph, you'd say, well, a sine graph starts in the middle going up. That middle going up has been shifted 5 units to the right, so I would write x minus 5. And now I have 3 different equations, all for the same graph. Now in part B of this one, it has an estimate, it has a couple estimate questions. So if it says estimate, that means you are free to give an educated guess. 22 would be right here. And if I go up to my graph and over, right, maybe my estimate would be 3 meters, 4 meters. How do you get an estimate wrong? You would get an estimate wrong if you said, I think it's close to 30 meters. That's way off, okay? So if you use your graph, go straight up, attempt a little bit better than I did at going straight across, okay? Look at the value and write down the answer. That would give you a good estimate. You can also get these values using technology. So if I go back to Desmos, I'm now going to type in this equation. So my equation was -15 2 pi divided by 20x plus 16. Scroll out a little bit there. There's our graph. And I can just say, I want my x value to be 22. That'll draw a horizontal line. We can click on the point. 3.8 is the actual answer, 3.865. That's an actual answer. We just did an estimate. Same thing in part C. So B. We should write down. What did I say? What did I guess? 5? Did I say 4? I want to say 4 because that seems closer now. So. So we did an estimate and we got an actual value. Same thing in part C. It says estimate at what time you'll be 20 meters above the ground. So I'd go to my graph, I'd label 20, and I go across, estimate this point, estimate this point. Okay, so I look down and I go, oh, I think it's maybe 6 and 14. Those will be my estimates. If I want to find out what it actually is, I can go to technology, type in y is 20. That'll draw that horizontal line. And 5.85 and 14.14. Those would be actual answers. Okay? For your calculator, for the green one here where it's x is 22, you could just type the equation and where the x is, substitute a 22. Right? Because if you have x is 22, you just have to plug in 22 for the x. That would find the value on your calculator as well. Your calculator doesn't have a good one for plugging in the y, so then the graphing calculator is better, because it's a bit of work to do the algebra when you're plugging in the 20 for the y and solve it. Ferris wheel story. If in my hometown of 1,600 people, they have a fair every year in August. And the town, I'm going to say already, about 50 years ago, the town bought a Ferris wheel. And every fair, they have 2 rides. They have a Ferris wheel, and then they have a ride with chairs that goes around in a circle, and a chair that goes out sideways, and then it comes back. So they have these 2 rides. And they've had the same 2 rides 50 years in a row. So if you love Ferris wheels, it is a great place to go for a Ferris wheel ride because you'll get the best, like as far as cost, it's super cheap, no lineups, because can you imagine if you have the same Ferris wheel for 50 years in a row, people are like, yeah, I've done that already. So there's no lineups. Anyways, about, I don't know, 5 or 6 years ago, I'm back in my hometown with my family for the fair. There's the Ferris wheel. I was like, I have to take you guys on the Ferris wheel. We go up. It's like only $1. Nobody's in the lineup. We get on the Ferris wheel. Go up to the top, come back down. Go up to the top, come back down. 5 minutes later, I'm like, please, somebody get in line. They're not letting us off. You just keep going around and around and around. Because on a normal ride, if you go to the Red River X, you'd be like, there's people waiting, right? And you're like, you do your ride and then they let you off, and then because somebody else has to get on. Nobody got in line. We're like, will it ever stop? You get to go. So if you really like Ferris wheels and you want a really long Ferris wheel ride, I'd recommend that one. If you're a little scared on the chair one, I don't know, 50 years, maybe those chains are starting to get rusty. You don't want to be like flying around and all of a sudden your chair flies off. Or, as was dangerous, one year, my cousin got on when he had the flu. Not a good idea, because you're spinning around fast. He was already a little sick. He started to feel more sick. In the middle of the ride, projectile vomit. Do you know what is really bad about a projectile vomit when you are traveling fast in the forward direction? It goes out momentarily and then comes back and hits you all over the place. Luckily, the people behind you just get little pieces of shrapnel. So, there's my Ferris wheel story. Yeah, and the other story. Okay. We're going to do one more. This is probably the hardest question as far as difficulty goes. Again, it's a tides question. They're telling you that it is periodic, so you know you can graph it with a sine or cosine graph, but this is the least amount of information that can be given to you to create a graph. They only tell you two things, a maximum point and a minimum point. So we start by graphing what we know. Okay, so we're going to put time down here and depth over here. And we know at 4:30 a.m. that it has a depth of 8. I mark 8 here, and 4:30, we're going to run into a little bit of trouble because if we type this into our calculator, do you know how to write 2 dots on your calculator for 4:30? No. All we have is a decimal place. So should we write 4.3? No. What should you write for 4:30? 4.5. Makes sense, right? Because it's half an hour. So this is not so bad. Now you have to figure out for me though, how am I going to write 10:42? 6 hours and 12 minutes later. Okay, so that's going to be about here, is going to be 10 point something. And we have to do a little bit of figuring out how we would change that to decimal. Now, how did you do 30 minutes? Well, your brain was just, it was so easy because 30 minutes was exactly half an hour. Why is it exactly half an hour? Because there's 60 minutes in an hour. So it makes sense that 30 out of 60 should be 0.5. Sometimes if you can, this is the thing about math, sometimes the easy ones you make so easy you don't even realize what you did. But they're the hint for figuring out the harder ones. For 42 minutes, I could do the same idea. If this is 0.5, well, 42 out of 60 minutes, what is that? And as far as mental math goes, maybe you'd say, oh, I can reduce that to 7 out of 10. Maybe that's easy to see that that's 0.7. So 1042 on my graph will be 10.7. And I have a maximum at 8, a minimum at 2, at 10.7. And these are the only points that were given. We know that it's supposed to make a sine graph. How do we take just 2 points and find all the rest? Well, one thing we could do is we could analyze that between here and here is 6.2 hours. And does that make sense that that will be half of the period? So if we go another 6.2 hours to 16.9, another 6.2 hours, we will be back at the maximum. I hope that you can also see that the center here will be at 5. We can draw our center line at y equals 5. And if this is one period, it needs to be separated into 4 equal sections. This is where our points on the center line will be. And now we have all 5 of those points. We have enough information to draw a sine or a cosine graph. To make the equation, we have to think about the dab part. Do we have enough information? Yes. What's our d value? 5. What's our amplitude? 3. Because it's 6.2 and 6.2, from one maximum to the other maximum would be 12.4. So we know our period. So we know that our d value is 2 pi over 12.4. Most typical equation would probably say, hey, let's start from our maximum. If we're doing a starting point from a maximum, that will be a cosine graph, a positive cosine graph. Our amplitude is 3, cos. Our period, 2 pi over 12.4. Our d value is plus 5. And a maximum is 4.5 to the right. Wow, that was close. X minus 4.5. I almost flipped the numbers there and wrote them in the wrong direction. I hate when I do that. I tend to only do that with students' marks who have like 81s and 90s. Second, we can make a graph for sine. Where does sine start? In the middle going up. So I find it in the middle going up. And I realize I have not marked that point on my x-axis. Does it make sense that if from 4.5 to 10.7 is 6.2, half of that would be 3.1. So this point would be at 13.8. And now I can draw my sine graph. Amplitude is still 3. Sine, period, is the same. So this will still be the same b value. D value is still 5. The only thing that's different is my starting point, and it is 13.8 to the right. So I get x minus 13.8. Nice. Now we got one equation in sine, one cosine. Sometimes people are like, ooh, could I go back 3.1 and use this point? Yes. If you wanted to use 1.4, that would work as well. Could I do a negative sine graph? Yes. Could I do a negative cos graph? Yes. Could I make Mr. JR's life miserable and figure out a point thousands of units to the right as a starting point? And he would have to check it. Yes. I would probably just mark it wrong, and then you'd have to come in and argue. And it would take you more time. That would be a good plan. I'd still give you the marks, but you'd have to come in and argue it at the end. I'm like, no, you idiot. 0. And then you come in, but it's actually right. I actually don't write you idiot on that. Just want to make sure. Okay, so we've got our two equations. This one has another estimate. It wants us to estimate at 130. So again, we have to figure out, well, what is 130 on the scale that I've done? 130 would be at 13.5. I go up and over estimate it to be at 4. If you wanted to find it out exactly, you could plug 13.5 in for x, either into the equation or use Desmos or a graphing calculator to do them. There are 2 questions at the bottom that you're to try on your own. As you get an answer, check with people around you if they got the same equations. And then you can ignore the homework listing at the bottom, but in your textbook, in section 6.7, you can circle the questions from 3 to 9. And I have tape up at the front. After you have graphed both the 2 that are try on your own, my suggestion is to go to section 6.7. So here's, I'll show you an example. Here I took a page in 6.7, and I took the paper that we just did, and I taped it to the edge. This still allows you to flip it over and see behind it, so you're not covering anything up. It folds nicely, and then it's in the right place in your notes. As far as when you're studying, it's not like, oh, where's this extra piece of paper I should study from? You can still use your entire textbook. So if you want to do that after you've done those 2 examples, I have tape here up at the front.